So, hello everyone. Welcome to another session of Coffee O'Clock. I'm your host Akash Kundu. I'm a PhD student at Polish Academy of Science. And today we have a very special guest, Michal Stekwe. And I'm sorry if I'm pronouncing it wrong, but I'm trying my best. And I guess most of you know him through his very descriptive and thoughtful blog posts, and also in the LinkedIn as well. And we also follow him all the time. Like whenever Michal posts something, we're like, okay, there is a Michal post. We have to go through it properly, because they are very interesting. And I'm sure like most of the people here reached out to him for suggestions, for, discussions and stuff, because he's a very interesting person as well. And he's a technical lead at Zapata Computing right now. And he's a researcher and software engineer. So, yeah, so Michal, the stage is all yours. Thank you for coming.
Cool. Thank you very much. Okay, so thank you for the invitation. Glad to be here. Some familiar faces here, so that's always nice to see that all those random people in the internet that reach out to me that become less random and are actually doing PhDs in quantum computing and whatever, and doing some amazing projects. It's really great to see this kind of community growing. And also yeah, I'm really like the idea of I know there's a lot of people in India who are interested in the topic, and glad that I can kind of put my kind of small brick in that community by participating here. So two things before we start. So first is okay, the format of this talk is a little bit experimental, and it might be a little bit chaotic, or I hope it will be good, but I think it will be maybe a little bit more conversational and than regular presentation, because I want to do kind of a whiteboard talk about this topic, and the whiteboard is my iPad and I'm screen sharing. But it's less structured than kind of presentation. So also I will have my notes on the screen, so if I kind of look in the weird places on camera, then sorry, I'm just probably looking at the screen. The other thing is I actually feel a little bit sick today, so if it might be the case that I would like to end a little bit earlier. I hope not, because after talking with you, it's I feel more energized, but just, I mean, if so, not my best day, so sorry for that. But with that being said, I wanted to talk with you about circuits. So before we get into the circuits themselves, why I'm even thinking about circuits. So there is basically this program that I'm a part of, which is run by DARPA. And DARPA is, okay, I will turn off camera not to be, it's then I look in the weird places. It looks weird. So there is this program called DARPA, and DARPA is this Defense Advanced Research Program, whatever, of United States. And they have this very interesting program where they try to...
Michal, sorry for interruption. Are you writing anything on the screen?
No, not yet.
Oh, okay. So sorry.
So they have, but good catch. They have this program where they try to evaluate, how useful future quantum computers will be. And basically, there are two parts of the program. So one part of the program is coming with application instances. So application instances are basically those, kind of problems that we would like to solve with a quantum computer. So for example, I don't know, this might be some, I don't know, some molecule, or something that we would like to calculate some properties of, right? And basically, so I'm not involved in that part. That's a different story. But the idea is that okay, they will come up with some problems that are important for for various reasons to solve, that are probably maybe good fit for quantum computers. And then we would like to figure out, okay, actually what quantum computer do we need to solve this problem? So we want to perform a resource estimation. So basically, there is, we take the problem, we make a, resource estimation, we take some model of like some quantum device, and then we get numbers such as, time it will take to run this, energy it will take to kind of run this type of calculations, maybe what's the like error rate of running it, like bunch of other different things. And well, I will tell you, like, performing resource estimation in general, it's like not an easy task. And in order to actually have something to resource estimate, there's like one thing missing from this picture, which is algorithm. So basically what happens is that, we take a problem, we choose, okay, this is the problem, we want to, find let's go with the classic, right? Find the lower energy of the lowest energy of the ground state for this particular molecule, because I don't know, like for whatever reasons, it's like important. We choose to use this particular algorithm, and once we have this algorithm, we can generate a circuit, right? And then we can create a resource estimate of that circuit using, like model of a quantum computer. And then we'll know, okay, for this molecule, given this algorithm, it will take us, I don't know, like a month to, of calculations to get the results, or it will take us 2 years, or like an hour, like, whatever. And this is important for multiple reasons. One reason is, well, it's still, not 100% clear what kind of problems quantum computers will be able to solve and will be kind of, useful for solving. Classical computing obviously is like, also developing all the time. So this is something that we would like to discover. And the other thing is, it's when you look at most of the papers with like resource estimations, it's really, there's like a bunch of assumptions going into doing any resource estimation, and it's like extremely hard thing to do. And therefore, we would like to have tools that can give us basically resource estimations with like better precision, smaller error bars. So we can actually say with certainty that, solving this problem would take this kind of hardware. And also then we can also steer the development of the hardware into particular direction, like showing that, for example, well, actually this is a bottleneck or that is a bottleneck. So this is something we should focus on. I don't know if you know, but there was this paper about FeMoco, right? And they have FeMoco is this molecule that is used for production of what's the word?
Nihal, I think
nitrogen.
Gaurav wants to ask a question because he raised his hand. Can you have?
Okay, I will just finish this and take the question. So there is like there was like FeMoco, right? And this is a molecule that's important for kind of production of fertilizer. Kent could make this, if we understand better how certain reactions go, we could understand much better, what's going, how to make this process more efficient. And therefore, they made like some resource estimations, but then it turned out that actually there were like a couple of subsequent papers that showed that, well, actually they got this part wrong. And then there was some other paper that showed that, well, actually, these resource estimates are like a little bit too optimistic here and here. And well, it's like kind of sucks because on one hand, you take a paper and, it's a decent paper, like the original FeMoco paper, like for sure. But it's not that like you can trust any resource estimates like published in like any paper. And it's also not that most of the people are not able to actually verify like whether this resource estimate was done like properly or not properly, because it requires like some crazy level of technical knowledge to do so. So this is kind of the problem that we're trying to solve in this DARPA program to some extent. Okay, Gaurav, you have a question?
Yeah, so just to clarify, when you say resource estimate, do you mean something like, finding the C naught count or or reducing the T count, or do you mean, finding how much entanglement is required to find the task or
So,
something else?
so I would say that like what a lot of people are doing where they do resource estimation is they, in this context, this is like this like T-gate count or like circuit depth and so on. But actually in this program, we go one step further and we translate, okay, like T-gate depth is like, it's something, but actually how this translates to like some value, like, some numbers that like regular person can understand, right? So like time, energy consumed or things like this. But I think, yeah, like number of T-gates will be kind of one of the numbers we'll be getting out of this. Yep, Akash?
Yeah, I had a like similar question with the resources. Because you said that there is a problem and you made this algorithm. So does this resource, this variables like T, E, or this epsilon, anything, it varies with the algorithm, or it
Oh
just?
yeah, absolutely. So this is, like basically the analogy I like to do is I like to talk about is like when you have an optimization problem and you have like an optimizer, right? And like classical continuous variable optimization, right? So you have like a quadratic function and you want to find where the minimum is. Well, depending on which algorithm you use, then you will get results in like different number of steps. You will use different number of computational resources to do that. And also, depending on like what parameters of the algorithm you will use, like step size in, gradient descent, right? It might make your algorithm, if it's too big, then like it will just like not converge ever. If it's too small, it will take a lot of time. And like this totally, affects, those resource estimates here. So it's like super tricky problem because on one hand you have, defining well the problem that you want to solve, which as anyone who ever worked on an applied science problem, they know that this is like 90% of the effort that can go into a project to define it well, the problem. Then you have to find the right algorithm for this problem. And well, then you have like know what's the method to actually produce the good resource estimates. So it's all like very tricky and ambitious.
Okay, thanks.
But we didn't really get into circuits yet, and like actually I was supposed to talk about circuits. So this is just like kind of setting the stage of like where I'm coming from at this problem of like why circuits are not necessarily the best kind of way to go with. Ooh, sorry, okay, good, sorry. So let's go forward and let's see what we actually do to get those resource estimates, because I think that's something that's important. Okay, so let's say we after we got the algorithm, right, we express the algorithm in like some way, right? So let's say we want to do QPE, right? So basically we can express the algorithm for quantum phase estimation in the following way. So the first step we do is, we prepare like those, two states, which is one is equal superposition and the other is like some kind of starting state. Then we perform a lot of controlled kind of unitaries that just are part of algorithm. Like don't worry too much about like what actually are the steps in the algorithm. It doesn't really matter. That's just like an example. It's like there are like certain steps that need to happen. Then we run the inverse QFT, and at the end, there is like measurements and post-processing. So that's basically how this algorithm goes. Like how we would usually, go to write this. Well, I would say usually we would go with a circuit, right? So we have something like that. And then this is the part, right, where we have like Hadamard gates to prepare the equal superposition, right? Here, there's like some state preparation, something that, is responsible for this part. Then there are all those like controlled unitaries. And I'm kind of missing the exponents here. It's like, they're coming with some exponents. So after that, right, we do this like QFT. And what, like this. Okay, and then we do some measurements at the end. Okay, I mean, that's a valid way to express this algorithm, right? Like a circuit. Okay, so actually, but it's kind of, you can't really express, like the problem is that like this is kind of still relatively high level representation. It's not like, this is circuit itself, because those blocks, like I know, like this or that, or these might be like some super complicated components, right? Like depending on like what this unitary matrix here is, it's like it might be like gigantic circuit with like millions of gates. So we actually need to compile that to something even more, like actual circuit, right? So this is like kind of block level representation, and then we aim to get into something more digestible. You cannot just like tell quantum computer, hey, here is, prepare me state psi. You need to say Hadamard, RZ rotation, RX rotation, like whatever. Right. So, okay. So how we do about compiling this algorithm into, well, something actually useful. Well, we start right with this like, and now I'm going through. This is the procedure that we actually use in our project. So we take this like abstract representation of the circuit, right? Then we have this block representation of the circuit. That I just shown, right? And then we compile this to a logical circuit, right? So logical circuit means in this context that this is something, this is a circuit that, well, assumes qubits are perfect and there are no errors and so on, right? So this is like idealized kind of logical circuits. Well, but we know that this is not something that will be running in on actual quantum computer, right? So we need to actually get this into the fault-tolerant quantum circuit, which requires some extra steps, right? So, for example, we take this logical circuit and we map it to gates, like a circuit that used only Clifford plus T gates. Then we use procedure called ICM to even further, like, refactor the circuit that we have. And then in actually the approach that we are following, we are expressing this, we're expressing the circuit as a graph, which represents, well, kind of algorithmic graph. Like this is a graph which represents a quantum state, which basically represents the algorithm. I don't want to get into the details of like how this actually works because it's pretty crazy and would take the whole talk just to scratch the surface. But what's important, then we can take this graph and then we can translate this graph into some fault tolerant compatible instructions. So later, perhaps we will translate that into an executable circuit, right? So it's like something that we can run on the actual machine. So the trick is that, as you can see, there's like a bunch of steps involved, and some of these steps are like wildly inefficient. So, for example, let's say that in our example we have this, we have the circuit, moment, right? And up, sorry, right? And we need to perform like operation like this. Okay. So this is how the inverse quantum Fourier transform works, right? Is that we are having some rotations here, and then basically this is kind of the first block, and then for the next block we are doing it again. So we have Hadamard and we have like some other rotations, right? And so on and so on, right? So as you can see, we have kind of two blocks of circuits, right? Which are very similar to each other because they are kind of created recursively. So this is for n equal 4. This is for 4. This is for n equal 3, and kind of the problem is that we can see with the circuit representation in this context is that if we are to perform kind of this transition here from kind of block-based to logical circuit, we'll end up with like some stupidly big circuit, and then we have to do this like all those subsequent steps. We need to do them for that huge circuit, but well, actually we don't need for like the for the purpose of doing the resource estimates, we actually don't necessarily need to do this whole compilation, because it's enough for us to know, for example, how a block like this, right? So this is this block. Maybe it's enough for us to know how this block translates straight to the graph. So maybe we only need to do this compilation for, kind of some abstract n, and do it once, and then we can kind of reuse this result like over and over again. So even more kind of blatant example would be if we had wouldn't happen for QPE, but like for example can happen in like truthorization, where for example like with QAOA, right? So with QAOA, we have something like this, e to the minus gamma 1 HC, then e to the minus beta 2 HB, then e to the minus gamma 2 HC, right? So we have these blocks, and obviously these two blocks are exactly the same when you compile them. The only thing that's different are those parameters beta and gamma. But like, if we first go and compile stuff to a regular circuit, well, then we kind of like to the logical circuit, then we are doing this compilation like twice, which is like wasteful. And like if we have like 100 of layers, we'll have like 100 of like identical blocks, different only by like parameters, that then we have compile all of them to this like, Clifford T, ICM and graph, which is just wasteful, because we could do this compilation, I don't know, like once for like symbolic parameters, and then just like substitute those params where we need them. So this is the place where I'm kind of coming from, where I noticed that representing circuits as like kind of quantum programs as circuits has like serious issues, just in the kind of compilation, just when it comes to compilation. And now I will get to like some other problems that when I started thinking about it and like talking with people, that there are like more problems. Okay, so there is a question in the chat. Which error correcting code are you using to make the logical circuit? I don't know, honestly. I think I don't know. I think we are. No, okay, I'm not able to answer this question. Sorry, that's probably the best answer I can have. Akash?
Yeah, I mean, I didn't understand like one thing. So consider you gave me this R block with n equal to 4, right? but I need to transfer it into graph, and you're saying that decomposing into Clifford T and then ICM and then graph is very resource consuming and stuff, right? It takes time. But then we have to decompose it once, right? To know what is inside this R block, right? So this is a huge thing. So we have to construct the circuit, because I'm a bit lost in this, because you're saying that you want to represent it as a graph, not decomposing into gates, right?
Yeah. So the thing is that, I mean, okay, like in some, let's say, like ideal world, I hope we could get kind of this, do it like this, for example, and just like know that, okay, for this block, we know like this block translates to this kind of graph. But well, that's probably not where we are. What I'm saying is, you don't necessarily need to compile, if you have like repeated blocks in the circuit, you don't necessarily compile each of them every single time. If it's like repeated 1,000 times, then you need to compile it once and then say, hey, kind of, I already did that. So, this transforms to like kind of this, subgraph, or like, this sub-circuit. And I just can express it as a for loop, right? And not as a circuit. Like I don't have like, for loops in a circuit. That's kind of the problem that we have here.
So you're saying like, sorry for interruption, like you're saying, I'm just trying to understand this, that if you have repeated blocks and stuff, then you can have a decomposition maybe on the first block, and all the other blocks can be predicted, right? Because they're repeating. So this reduces the resource, right? Because you don't need to decompose all of it, just a part of it, right? This is what you're saying.
Yeah.
Okay. Perfect. Yeah. Thanks.
Okay. So so this is like one of the kind of problems.
Sorry, Michael, I have a quick question.
Yeah, sure.
I'm sorry, my video is somehow not working.
No worries.
So isn't what you're telling us, isn't this the basic idea of, well, not the basic idea per se, but isn't this the idea of, using the programmable processors and then using feedback loops, like for example, whatever result you get, and then suppose you have to use the programmable processor multiple times because that's the processor that is available to you. For example, in this case, it is the R with n equal to 4, and then you just use it multiple times as per you need. I mean, isn't basically, I would say the fixed programmable processor works on a similar idea, right?
Maybe. Yeah, I think that's kind of reasonable analogy.
Okay.
I'm not sure about the details, but like I think in spirit, yeah.
Okay.
Yeah. Okay. So now I would like to kind of get maybe a little bit beyond this motivating example that took me half an hour to explain. But I think it's good because it's like I will have things to refer to. So there are like a bunch of issues with the circuits, and I basically described some of them in the blog post. But so I will be like repeating myself a little bit, but hopefully with more context, it will be useful. So one problem is with circuits. Oh, and by the way, I like by no means think this is something. How to say that? Like, there's something like some people in the community have been thinking about like for a long time, and this is also something that definitely some of the ideas here and the problems, they don't come necessarily from kind of my own kind of thoughts or research. It's like from discussions with like a bunch of people. So just like there's like too many people to acknowledge, because like I talk with that about like a lot of folks. But so I think it's not, well, what I'm saying is like probably not like super novel, but I hope it's like helpful to kind of list these things out and like categorize them, like to actually see what's the state of the state of the issue. So first problem is expressivity. So, well, you just like can't express like you can like, so you can express a lot of ideas with circuits, but it's not the best tool for expressing ideas. And like I would say the analog is with like assembler, right? Like you need to have right tools for solving the right problems. Like you don't want to use, write some like hardcore high-level algorithms in assembler because, well, in principle you could, but it's just like not good tool for solving this kind of problems. You want to have like higher level languages, right? At the same time, it doesn't make sense to write, doesn't necessarily make sense to write like some super low level embedded programs in Python because, well, probably assembler or like some other low level language is just like much better. And with the algorithms, what like I've seen looking at what people are like, how people are working on developing algorithms, like usually they don't care a lot about this like low level implementation of gates. So for example, we had that like something that like annoys me is you cannot with circuits, like hard to express certain ideas. So if I want to create a equal superposition of, on 4 qubits, I'm using Hadamard gates, right? That's cool. But I'm actually not telling anyone, hey, I want to create equal superposition. Like if I want to change the measurement basis, I will also use Hadamard gate and then do the measurement, right? But that's the same Hadamard gate. It's like, it doesn't express the intent. So what I would much more like to have is I would like to have, well, like a block which tells me, equal superposition, right? And be able to express this idea in some like programming language or whatever, or have a block which says, change kind of measurement base, right? Rather than explicitly using Hadamard gate that like, okay, this is what you need to do. And why I think it's important, like first, it reduces, it's like makes things simpler to read, simpler to understand. Like I've definitely been in a situation where I'm reading a paper and in this paper, there's like, the snippet of the circuit and like looking at this and like, why the hell they have this like rotations here and like those Hadamards here and the CNOT, like, oh, okay. Like here they like are changing base and here they just like want to entangle these qubits, right? But, it's not important that it's implemented through a Hadamard or through something else. It's like, it's implementation detail. Like the intent is like not clear in a lot of cases. And another risk is that it also limits the possibility of like, like using different platforms, like using different hardwares. Because if you, for example, even though the kind of regular gate-based quantum computing is the most popular, you can have different types of gates. You can have different, I would say that. For example, like Xanadu was working, I don't know if they still do, but they had this like continuous variable quantum computing kind of framework, and they had like totally different gates there. So if I have a algorithm which is expressed as circuit using these standard gates, if I want to use it for anything else, then I have to understand what was the intention and then like, transpile this to like a different language. And if I was using this like green representation, right, then I could have like an automatic compiler that like compiles it to what's kind of best for particular platform. So, that's kind of one issue. Oh, and another thing is so in certain algorithms you want to do operations like basic operations like okay, oh sorry, that's like a different one. So in math, like I think if you want to add a couple of numbers, right, so for example like 5 plus 5 plus 5 plus 5 plus 5 plus 5, right? I mean, no one writes it like this. I mean, it's stupid. What you want to write is you want to write like 6 times 5, right? I mean, that's like simpler, and like we're not like kind of killing ourselves with writing everything. We just use better notation. If I want to say 5 times 5 times 5 times 5 times 5, I'm saying 5 to the power of 5, right? And I'm not like explicitly writing all those 10s or 5s or whatever and like adding them. So imagine doing math if you didn't have multiplication and you had to explicitly write like addition everywhere. It's just like stupid, right? So, and I think we're like a little bit like with this with circuits. It's like we just like, we're just like using those like very low level operations to express some higher level ideas, and like that's not the best way to go. Okay, Palash?
Hey, so I was just curious on how we would. So it's an interesting idea that instead of writing edge gates, which are the technical and low-level representations of a gate, you replace it with a label or a name that is the purpose of the gate, so that when you're reading, you not only know it's not only more readable, it's also more platform independent, because then the platform while compiling, it can decide what the best gate is to do that operation. But my question is, what if this mapping from technical gate to usage is not accurate? One gate can be used for many things. Edge gate can be used for entanglement. That is true. That is in entangler, but I said it's also a phase changer. I mean, I'm just curious, like, what if the mapping from a technical, like a low-level gate to your label is not like there doesn't exist one mapping for that.
Yeah, I mean that's a good point. I mean, I think that so I think in certain algorithms, especially in variation algorithms, there is this, people have those like entangling gates, and they use certain gates to like entangle two qubits, right? And they do that. They the choice of the entangling gate depends on the platform, like actual hardware they are running on. So like sometimes they use CNOT, but like sometimes you don't have CNOT on this, so you would use like ISWAP or like something else. And honestly, it like doesn't matter which one you use, because you just want to entangle, and the, like, the intent is to entangle, and then like maybe do some extra steps. So maybe sometimes I think the fact that you have, again, I'm definitely not sure about it, but I think like sometimes the fact that you might have not kind of bijection mapping is not really a big problem. And for example, in case of this like graphs that we are we are creating here, you can translate given circuit into multiple graphs, and that's good because later, for like whatever reasons, you might want to have a more sparse or more dense graph. You want to minimize number of edges or number of nodes, and like do different operations like this, and like perform optimization like at a different level. So I would say, and like it might be same here, that you might have kind of different ways to change the basis of measurements. One is using Hadamard gate, another one is using, I don't know, 2 rotation gates. And like for whatever stupid kind of hardware reason, using 2 gates might be, I don't know, like better in this case, because you can make them more precise or whatever. Or you just have like custom pools that is not that you have implemented that like performs this operation. It's like a little bit silly in like super simple operations like base changes, like change bases, or with like Hadamard gate. But when you get into like some operations that take a couple of gates, there are like so many different ways to implement that it's not the problem that there's no one-to-one mapping. It's actually kind of helpful that you have more degrees of freedom.
All right, so you're saying basically the intent is not to use, you're not using edge gate for the sake of using edge gate. We are using it to do a certain intent, right? The intent being change phase or entangle. So as long as we can have building blocks that represent intents, the compiler can handle what hardware to compile that intent to.
Yeah. Cool. So another problem with circuits. it's okay. Like, one moment. Oh yeah, I kind of covered that. So what I wanted to say is that circuits are like too low level for like certain uses, and this is kind of the point here, right? Like you don't want to necessarily express the things with like addition if you want to do like powers of number, because that's like inconvenient, and like same with circuits. Also, another problem is that on the software side, if we are using like really like developing, it's like a little bit tricky, but if you're developing like fault tolerant algorithms today, like surely you cannot run them. I mean, I agree with that, but you want to explore them, research them, or whatever. Then, using if you have expressed them as circuits in your computer, these objects get super big pretty quickly, and it's very hard to work with like such a big data structures. Again, as I mentioned before, having those like repeated blocks, if you explicitly translate every trotter step to a circuit, then you have like some crazy, with like 100 steps, you will have like some crazy big circuit that like takes time to process, takes memory to store, and so on, which is like not very practical. Okay, so another issue is, I would say, classical control flow. Right, so basically it's not super easy with circuits to implement to like express certain operations that you might want to have in the algorithms, like if statements. So imagine, right? So let's say, I want to do, I have a circuit, right? I have a circuit and it's like doing, I don't know, like something, ZX, like C0, whatever, right? Something. And then suddenly I want to measure, this qubit, and kind of I'm doing this like mid-circuit measurement. And depending on whether the output of this is 0 or 1, well, I'm either going forward with, if it's 0, I want to go forward with like Hadamard and X, and then I don't know, like Z gate on this qubit. And if it's 1, I want to go with like, I don't know, like C0, right? Because anyway, this is something that you get in quantum error correction. Like depending on like what you measure, what's the syndrome that you measure, you want to apply different gates to correct for that error, right? But it can also be used algorithmically. So like, how would you express that as a circuit? It's like you have like clear, branching structure. And I honestly, I have no idea how to express this as a circuit in a reasonable way. I think there is no reasonable way to do that. So, well, you simply cannot use circuit to express certain algorithms. In the runtime, you will do the measurement and like effectively go with one or the other branch, like sure. So what you will execute in the end will be, will be expressed as circuit, but you don't know which path you go before you actually run the circuit. So that's like a huge problem, I think. And yeah, I mean, that's it. Like basically, that's a big issue. I could probably like, I'm not that familiar with like what are some other useful classical control flow operations that people do in quantum computing, like in quantum algorithms, but I bet there are like way more that are tricky, and that also circuits don't allow to do. Yeah, another thing is, I think that I already touched on that, is, what about non-gate based kind of paradigms? So I was talking with Jonathan Wurtz, if you like kind of are interested in QAOA and you don't know Jonathan Wirtz's work, then I like absolutely kind of go and read his papers. That I really love them. Like learned a lot from his work. And right now he's working at QERA, and QERA has okay. I hope what I will say is true. I think they have like neutral atoms, and basically they have this like it's not qubit based. It's like simulation. It's simulating quantum system. And from what we talked, it seems that you have QAOA, and QAOA as we know looks like this. Right, and that's kind of the essence of QAOA, right? I mean, start like on some like plus state or whatever, and actually, if you express this like with this format, you could implement that fairly easily on QERA's platform. Because they can do time evolution of Hamiltonians parameterized, and kind of that's what their hardware is doing. Like it's designed to do it, like perform this type of operations. But the problem is that if you go into any kind of existing software, you actually get translate this into gates, into a circuit, because kind of that's how this works. Like we compile everything to circuits. And the problem is, like, if they get a circuit like this, they have to compile it back to figure out what the exponent, like what these Hamiltonians and the exponents were, and only then they can run it on their machine. So it's, I would say, like, using circuits is also somewhat like, discriminating like other platforms. I think there's a lot of stuff on with quantum annealing, adiabatic quantum computing, QAOA, which are all kind of the same family. I think if we had some good software abstraction kind of in between, like math, right, like here, math and circuits, like that would allow us to express these algorithms better. I think it will help with being able to be more cross-platform, and even I think think about these things more clearly. Truth is, I think most of the people who work on QAOA don't think about QAOA in terms of circuits, because that's kind of too low level for QAOA for sure. But still, when it comes to writing software, and I think that's like one of my kind of main points or problems with circuits is that we have ways to express algorithms in a different way, but on paper, like, we don't have really good ways to express them in software, and we don't have like a standardized ways to express them in software. So that it's like slowing down development of the algorithms. Okay, so I think this is enough me ranting on the circuits, and I wanted to say that I think like most of what I said is correct, but I'm not like 100% sure about it. So definitely, like, filter that through your own kind of perspective. Now I wanted to say, okay, there are like two more kind of bigger topics here I wanted to talk about. Like, one is, why circuits are not bad, and second is, where, like, what are some suggestions, like where we could go. So why circuits are actually good. I mean, circuits are a useful tool, and sorry, I mean, like, my blog post was like a little bit clickbaity with the title, and like, like some people, I try to convey the message like circuits are not actually that terrible. They have their like kind of place in the grand scheme of things, but like some people, I mean, rightfully so, were telling me that, well, but actually you're saying like circuits are bad. And then you were saying maybe not that bad. So what the hell do you want? And like, it's a little bit confusing. So to clear things up, well, circuits are definitely good tool for certain things. So for example, we are in such days of quantum computing that if you want to actually run something on hardware, well, you have to deal with circuits because, come on, like, like we are like you cannot run like super complicated algorithms with like really huge depth, and you need to, and the hardware is really crappy, so you need to fine tune kind of by hand the circuits that you have and like make sure that they're the right circuits for particular hardware and so on and so on, right? And also circuits give you this and like, I think like don't abstract certain aspects of hardware away as like math, like, how we would express the QA way here would. So yeah, like definitely if you are working on things that are more low level and like more, I want to run some programs, today, I think circuits are good way to go. I think they're a good way to explain certain concepts in like education and so on and so on. I think the problem starts when you start looking more ahead and you're thinking about more like, algorithms of the future, or like doing things like compilation, resource estimation. Then like in these realms, circuits may not be the best. I also think that like actually when it comes to education, they're like good to explain some concepts, but they make some other concepts like overly complicated, and it's just like, I don't know. I think if you like totally ditch circuits model, then maybe it would be easier to explain certain things, because we would like think harder about more natural ways to express. I think an example of that, it could be, and again that it ties into this like non-gate based problem is measurement-based quantum computing. It's like measurement-based quantum computing I not understand it very well, but as far as I understand, you can always translate this into a circuit, but actually it's doing kind of very different things than what circuits were, designed for. And there are like certain algorithms or certain concepts that would just can be easier explained from the perspective of measurement-based quantum computing, and we are not really doing that because we are teaching people mostly only about circuits. I mean, there are reasons for that, like sure, but I just want to say that, yeah, that's kind of another issue. So circuits have their use, and it's not that we should get rid of circuits. My point is we should probably think about better ways to express quantum algorithms and just like experiment a little bit more, and maybe not assume, take them for granted in some sense, and just like use them without any reflection, because I think there are like other ways to that would just like unblock ourselves when it comes to like development of the quantum algorithms. Okay. Before I go into what I think are kind of some alternatives to circuits, or how we kind of should, what I think like would be the way forward with this issue. Any questions?
Yeah, I have a question, or maybe it's a doubt mostly, because
Sure.
if you go up there, when you wrote that you need to change your basis and stuff with these blocks, right? And then you give this example of Xanadu and then gate based and stuff, right? Because they're different gates. So what I understood is that, consider I want to make an algorithm in Xanadu, okay, in their surface, like in their platform, then I will make in such a way that it will be compatible for them, right? But then in your block, you are saying that this block will also translate everything. It doesn't matter if it is like run on like photonic based or ion based, it doesn't matter. So that means it need to have information about all these decodings, right? Like this block.
No. I mean, block doesn't need to have that information. You need to have a compiler. You need to have a tool that will allow you to translate that block into particular platform that you're using, right? But so basically, you know, like you have a blog which does, I don't know, I say like QA, right? I mean, whatever. And you want to have a compiler that will allow you to compile it to kind of gate-based quantum computer. Oh my God, that's not legible at all. Gate-based QC, right? It will allow you to translate it into like continuous variables quantum computer, into like neutral atoms quantum computer, or I don't know, like something else. So, well, this line, right, here is like a lot of software.
Yeah.
It's not necessarily like you need to have a tool which allows you to do that, right? Like the problem is like right now, what I think like most of the time you end up expressing your program like this, and well, you need to do kind of this translation, or even kind of this, you know, going like this. And you are losing like intent. You are using what you actually meant by these. Maybe you wanted to, you know, like maybe there is a quantum computer that just allows you to initialize in future, right? Allows you to initialize stuff in like equal superposition. Like, okay, like now if you express this at Hadamard gates, then you need to kind of add a piece of software that tells you if I have Hadamard gates at the beginning of the circuits, that actually means that I need to initialize them in an equal superposition, which is like a little bit of like, you know, kind of reverse engineering of like what author kind of was thinking. And if we explicitly have something that says equal superposition and then compile this either on the gate-based computer, where you need to put a Hadamard here, or some other thing where you can just like start your state from this kind of equal superposition, well, that's kind of implementation details, right?
Okay, yeah, this is really.
Okay, this question?
Yeah, I had a question. So I found this if statement example very interesting. And so I'm just curious, so if you actually were able to implement this quantum if statement of sorts, then physically would that require like multiple copies of hardware, or like say lots of ancillas? Like,
oh no, I mean, okay, so there are like two things, right? So one is that I bet you can do that in kind of circuits in a way which is kind of wasteful, right? So I think you could do something like that where, okay, sorry, I'll just go with like something, right? And then you do like measurement.
Yeah.
And based on this measurement, well, now it's like logical, you know, kind of either one or two, right? So then based on this measurement, you put like some CNOT into kind of bunch of ancillas, and or that's actually the other way around. Sorry. Well, you can do this, and then like either, you know, and then like either perform some operations like here, or like some other operations here. Well, but then you have like plenty of ancillas that are actually unnecessary, because what you could have done is like on the runtime, you could send this information to like CPU, and CPU tells you, okay, if it's 1, then I want to perform like operation 1. If it's 0, I want to perform operation 0, and then tell you, okay, this equals, you know, X Hadamard, and this equals whatever, like Y Hadamard, right? And then it tells your computer in the runtime, because, you know, this is time, right? So this is like time passing. So you can say, okay, now I'm either implementing like XH or I'm implementing YH, right? I mean, either or, but I'm doing that on the same qubits that I already have, and I don't need to do like bazillion ancillas to propagate them, information through the circuit.
But in that case, the CPU itself is like classical control, right?
Yeah, totally.
Yeah, it's interesting.
And
But
there are algorithms that do that with like that use this kind of scheme. I mean, I totally agree that there are like other algorithms where adding plenty of ancillas and doing that through more kind of quantum computing's way is also like valid, and it's like good way to go. And not to mention all the kind of implementation details, how you do all this, but certainly, it's having ability to do this kind of mid-circuit measurement is also useful.
right. Okay, yeah, that makes sense. Yeah, thanks.
Cool. Okay, so I wanted to tell you a little bit about what are my thoughts about thoughts how to move forward. So I think that it's like there are like definitely people who are thinking about it hard, and they develop those like higher level quantum computing programming languages, because in the end that's what it boils down to. Like, you want to have high level quantum programming language, right? And that then has like this layer of compilation, and it will be compiled to whatever executable thing is. So, and I think there might be people that like already solved this problem. And yeah, I mean, that's totally fine. I think there is not one solution that kind of solves all the issues. But basically, I think we should start experimenting. I mean, okay, it's like I'm coming, okay, like I was talking with different people about it, right? And I was talking with some people from like some national labs in US, and like it seems to me that like for them, it's kind of, yeah, sure, we have this like particular high level language that we are using to express our algorithms, and like we are using it for like 5 years already, and like it's cool and it's good, and like, it's like solve all those problems. But like I have this feeling that even though there are like some people who've been in the field very long, and this problem is obvious to some of them, or like some aspects of this problem is obvious, then there are like people like I would say, more like early in their quantum computing journey that are totally oblivious to kind of this kind of issues. And people who are, just like starting to learn quantum computing, they're like playing with like Qiskit, Pendelane, whatever, and they just kind of never challenge the idea of circuits, and they just never occurred to them that, well, maybe there's a better way to kind of express my ideas, and like there's maybe something interesting to work on here, right? So I feel like there is some, I don't know, like disconnect to some extent between some group of like specialists who kind of work on that or figure this out, or are just like programming languages nerds that like this type of things, and then like a lot of people that just are doing some projects in quantum computing and well, could have much better tools to do that, but they don't, because like those tools are maybe not like very popular, or like this problem is not very popular. And because in principle, like all the frameworks, like I don't know, like Qiskit, Cirq, Pendelane, like whatever, they're actually kind of doing the same thing, and they're like kind of working in the same paradigm. And then you have a bunch of other projects where it's like QSharp, Silk, I don't know, like Project Q, Quipper, which are those like more high level things. But what I feel is that like they're like not very kind of introductory, as like not a lot of people kind of know them well or like use them on a daily basis, because these other paradigms are just so much more prevalent kind of for what people use. And so my real kind of intention here is to just like be a little bit like thought-provoking and maybe encourage you to check out some of those other projects. Maybe you will find the way that I don't know, like QSharp expresses algorithms, or like Silk or whatever, to be particularly, good for your project, or maybe you'll see how it works. You'll see that like, whatever, it's like way too complicated. And then like 2 years from now, you'll be working on some project and you'll see, oh, actually now I appreciate those kind of design decisions that they made in that other language. And like, I want to spend some time and just like, develop my ideas in using that language. I was thinking initially when I was also writing this blog post, and it's like that, there's like a lot of things. So I was thinking that, yeah, it would be nice to have some common data structures to express these things, maybe have some common abstractions for, building blocks that are used everywhere in like all, in plenty of algorithms. So I don't know, like, QFT, right? I mean, you basically should be able to like just like put a QFT block in your circuit and it should work. And like some languages offer you that. But then like I also like some people told me, which I think is like very fair point that I haven't thought about, is, hey, but we have like plenty of classical programming languages. So what the fuss is all about, like, you don't have complete interoperability in the classical world. So why would you like to have complete interoperability of like, different ways of expressing algorithms in quantum world? In the end, it's like all gets, compiled to machine code in one way or another. So like, sure, you can execute those things. But when it comes to like expressing those ideas, maybe it's fine that, one person will use, as it is fine that like one group is writing their code in Python, the other is writing in Julia. And well, it takes effort to translate between these two. Maybe it's fine like one group will be writing stuff in Silk and the other in, I don't know, Q#, and it's not trivial to actually, transverse those ideas. So yeah, that's kind of some random thoughts on the topic. So what do I have here? Oh, I wanted to absolutely, talk about this because like some challenges in addressing this. It's like famous XKCD. I'll just give time to read. Won't be reading this, out loud. So, like this is also a situation that we don't want to end up in. Like on one hand, you want to, there is like a reason some people prefer object-oriented programming and some other people prefer like functional programming or like something else. And you surely can like express different things in different languages. Like, they have like different uses. At the same time, I feel like it's like super fragmented right now. There's like a couple of, small groups working on those like languages, and not that many people are actually using them. And this is, something that helps to get us into this situation where there's like plenty of competing standards, which are totally not interoperable. Maybe there should be, I don't know, like maybe there should be some layer of compatibility, like something that like, I don't know if you know QIR, quantum intermediate representation. These people are doing some amazing stuff, but on I would say like lower level. So basically their idea is like whether you come up with like a circuit or you come up with like something else, if you have kind of a transpiler that allows you to translate that in like QIR code, then you can run these like QIR programs on like multiple different platforms. And QIR is like great project, and it addresses like some of the issues I've been talking about here, especially when it comes to like compilation and interoperability. But at the same time, it doesn't, it's not high level. It's like, it's intended to be machine to machine. It's like intended to be non-human readable. It's like LLVM basically. So I think like we should have like some higher level, like interfaces for quantum computing that would be useful. Okay, a question about quantum computing from perspective of automata and formal language theory. I know that Abu Yakarilimas from from Latvia and wait, what was the name of the university? I don't remember. Like from QWorld was working on this kind of stuff, and I think I talked with him a little bit. I think in this podcast, so you can check the link out. Yeah, and I know I'm kind of rambling a little bit at this point. Sorry for that. Okay, so two things that are maybe a little bit more concrete before I finish. So one is, okay, like, so what do I think the solution to this problem should have, right? So, well, it should be definitely something in software, because there are like a lot of nice concepts, but some concepts are just when you try to implement that in software, it like falls apart. It's like, it turns out it's like wasn't actually that good of an idea. I think it should be something that's like to some extent hierarchical. I don't know how I think that's the spelling, and hierarchical and composable, so that you can basically like combine those different blocks in like different level. Human friendly, like for sure. I mean, as far as like programming languages, some are totally not human friendly, but we still use them. Like I wouldn't consider like C particularly human friendly, but I also understand how it's like way more human friendly than like assembler, right? So sure, like but like saying like like kind of gates are not very human friendly to read. Like this is assembly basically of quantum computers. Another thing that like someone pointed out to me, that we should use registers, and like this should be something that like you don't have to, like, you shouldn't have to deal with like the concept of like single qubits. You should have abstraction for like registers, as similarly as in like classical computing, you kind of have different, you don't really play that much with like single bytes. Bits. Usually, at least you kind of do operations bytes and whatsoever. And also, yeah, definitely something that's like interoperable with like different frameworks. Like it should be usable with gate-based system. Yeah, question?
Yeah, you asking me?
Yeah.
Yeah, I just had one question. Like I understand, like based on all of you that you've talked about, which is like it seems to be very closely modeled on how classical computation developed, right?
Mm-hmm.
That if you think about it, like there were like people thought of gates and then transistors, and then they built circuitry and then algorithms based on that. But I just think that, so for example, consider the example of registers or I think like I'm just curious, do you think there is any way we are probably limiting ourselves in how we think about quantum algorithms because we're modeling the thing on how classical computation developed?
Yeah, absolutely. I mean, I'm 100% sure that we are not getting as much. Can you mute yourself because I hear echo? Thanks. I'm 100% sure we are not getting like plenty of interesting kind of algorithms because we are just like trying to think in certain ways. So yeah, like I think like the tools that you use kind of shape the way you think, and like I think like it's not necessarily shaped very well Like, I mean, it's useful for certain things, but like probably not for some others. So the question is, do variational circuits require specific ways to be entangled from perspective of machine learning? I think not. I mean, in some sense, not really. Like with variational, I think like with variational quantum algorithms, it's a little bit like certain, whether you use certain gates there doesn't matter. I mean, some gates matter a lot. Some gates like don't matter that much because, well, they're parameterized. So like certain things can be always kind of compensated by using different parameters. So, you know, for example, okay, I'm very bad with kind of doing unitary matrices kind of in my head, but I think if you have something like that, like Hadamard and XGate, okay, like let's say something like this. I mean, this Hadamard here is redundant because you can always set the parameters in such way that you kind of incorporate that Hadamard into like one of these rotations. So in some sense, for variational algorithms, I think, you know, like expressing them with gates is
Hi.
sometimes might cause some issues. Okay. And the last thing, like when it comes to like developing this, some challenges that I see is like one is like the kind of proliferation of standard is definitely not a good thing, as already kind of XKCD shows that very well. Two other problems that I'm afraid of. One is technological lock-in. So basically, if we use very suboptimal abstraction, it becomes too popular, it will persist even though it's bad. And like think about my favorite kind of example of that is with keyboards. So you have a QWERTY keyboard, right? And this is like very bad design. It was like explicitly designed to be not kind of convenient. And people came up with like much better designs for the keyboard that allows to, you know, be more efficient in writing and just like, you know, more precise or like, you know, just like better. But for some reason, like we got the QWERTY got so popular that like other keyboards never replaced QWERTY. So we are now in the world when, because of like some random, you know, decisions of like people who were developing keyboards like 100 years ago, we use like extremely suboptimal keyboard design. And I'm afraid like, you know, something like this might happen if like people are not thinking about it consciously. Might happen here where we'll just end up with like representation for quantum computers that's like very suboptimal just because kind of it happened this way. And another thing is that, yeah, I also think it's like kind of delicate. The different use cases will require different abstractions. I know, Akash, I know. Different use cases require different abstractions, and therefore it's like something that it's important to keep in mind. You know, like the fact that, I know, you are working on variational algorithms doesn't mean that that's kind of all the algorithms are like that, right? The fact that you are working on like fault-tolerant algorithms doesn't mean that like all the algorithms kind of have the same issues. So probably there will be different solutions that are more tailored towards kind of different use cases. I don't know, and just like it's useful to kind of remember that it's like just easy to kind of get deep into your own work and like forget that there are like other ways people are, you know, thinking and expressing their thoughts, and like they're maybe just like facing very different problems. I personally like this, like software engineering. I see like the way you do research projects is like so much different from the way you build kind of lasting kind of products and like libraries, from the way you do, I don't know, like customer projects. They're just like the same methods that like work very well in one context for developing software, just like totally don't work in the other. And there are like valid reasons for that. Yeah. So I guess that's mostly what I wanted to say. So now I'm like open for discussion.
Yeah, thank you, Mihal, for the very interesting talk and very interactive, for making it very interactive, It was really, really interesting. So I'm just thinking that, so this is gate-based, right? What are your thoughts on quantum annealing?
On what?
Like quantum annealing, not like the gate-based ones.
Yeah.
Because they are also quite abstract, right?
I don't have too much thoughts on quantum annealing. I mean, it's like a different paradigm. I think you can. I think it's. I think like one thing I don't like. Okay, like so one thing I don't like about quantum annealing is that there's basically only one company in the world doing that, which is kind of unfortunate because everything is like very like it gets. If you talk about quantum annealing, everyone knows you are kind of talking about D-wave. It's like harder to talk about it in abstract, as it's like easier to mix kind of talking about quantum annealing with talking about D-wave. So for example, if D-wave hardware is bad, then you might say quantum annealing is bad, but that's not necessarily that might be this hardware implementation might be bad. I mean, I'm not saying it's bad. I just like I don't have much thoughts on that. But no, I think it's like for me at least, like understanding adiabatic quantum computing was like very interesting, and kind of connection between AQC and like annealing and QAOA.
Yeah,
it's I like sometimes I read some of those papers about D-wave, like so some annealing experiments, and I think that's the case. Like certain ideas that are very obvious for quantum annealing are not obvious if you look at like QAOA, even though they can be translated like easily. But like if you look at the algorithm from the perspective of QAOA, it's like I don't know, like certain things just like don't come to mind. And when I see the same picture in like quantum annealing, it's like it like feels more natural. I am thinking more like about schedules, about kind of optimizing the how we call that? Oh my god. Yeah, like optimizing the schedules and when to like turn on and off like the fields and like how to perform the annealing. This is So I'm sorry, I'm rambling. But basically my thoughts are this is like one of the going back to kind of the premise of the talk. I think this is like a good example of like how having different framework for thinking about the algorithm might be helpful with like coming up with ideas.
Yeah.
Okay.
So we have two questions here.
Yeah.
Can you tell about how VQC, I think variational quantum circuits are to be designed for machine learning?
Don't fully understand the question. So if you elaborate, I would be glad.
Yeah, I mean, you can unmute yourself. And there is another question like...
hello. Can you hear me?
Yeah.
So my question was basically how the variational quantum circuits have to be designed to be trained for machine learning.
Yeah, but like what do you mean by that?
How there are two perspectives. First is where we store the data first. Thereafter, we use the variational circuit for training purpose. So in variational circuit, we use some kind of different gates combination, and then we entangle them, and then we use a particular theta value to be trained for. So if there is anything like, because when I'm training a circuit, it's giving a constant learning rate. It's like stuck around 59% or rather 58%, but it's not giving accuracy more than that.
Yeah, I mean, like in my personal like kind of view, variational algorithms are basically like VQAs are basically machine learning models. It's like you can, I mean, it's like not that simple, but like you can view them this way, and like it's totally you can treat them as like parameterized black box, that gives you certain output, and it's like exactly the same as like neural network. And like, I mean, you don't need to know what's happening inside. So in this sense, I would say that there is this correspondence.
And also, like, don't you think, like, at the same time, if you have a variational quantum algorithm and a constant architecture of circuit, like considered for variational quantum eigensolver, right? Then that particular circuit has a specific minima, right? I mean, maybe it is not global, right? So maybe it is getting stuck there because the architecture is not efficient, right? So we have to try and try, right?
Yeah, totally. I mean, it's like you can easily see that with QAOA, where for like one layer, you just like don't reach. If you like make a full scan of one layer QAOA landscape, you see that the minimum doesn't correspond to the global minimum because you just cannot express like the state which is the correct solution cannot be expressed by this circuit. So if you add more layers, then you finally get there. There's plenty of good literature on the topic, that I'm not kind of that deep into that. So Rishabh had a question. Could you please elaborate on why different use cases need different abstractions? Sure. So I think a good example is databases, like classical databases, where like depending on like what's the most common operation you are doing, you might want to use different database. So for example, if you are, I know, like, okay, I'm not that good in databases, but basically if you are running some, I don't know, like statistics on the results, and you are want to retrieve okay, what's the average price of that product or whatever, then, well, relational database is a good place to store this kind of information because it's easy to go through the table row by row, like select the labels, like and run some averages and whatever. But if you want to explore more like relations between objects, then maybe some graph-based database is much better, right? Because you can just like find the node and like follow each node, like where it links to some other nodes, which might be very inefficient in relational database, depending on like particular use case. But I think this is like an example where different use cases will use different abstractions, and again, it's easier in classical because like these are better established than in quantum, I think. Okay.
Okay, so let's take one last question by Priyam because he has his raised hand. Yeah, please, Priyam.
Yeah. So as you build these higher levels of abstraction, I was wondering, how do you think about quantum advantage? So in the circuit model, you can think about quantum advantage in terms of what is the cost of classically simulating a quantum circuit, right? And so for Clifford circuits using stabilizer formalism, you know that it's efficient. But as you build these higher abstractions, how do you think about which circuits are efficiently simulatable classically and which are not? Like,
sure. I mean, it kind of boils down to this picture. It's like you need to, okay, like one thing is like, in order to get some better idea, I guess you need to just like traverse a bunch of layers of abstractions.
Right.
And I think that's like one thing. Another thing is that I feel, that it might be easier, like, for example, like for QAOA, like it might be easier to reason about quantum advantage or not from the representation here rather than from circuit representation.
Nice.
Not that I have particular thoughts about it, but it's like in principle, right? Like these equations are like kind of can be easier to reason about. So yeah.
Yeah, but like sort of broadly, it's still kind of very open-ended and interesting to think about, I guess. Yeah.
Oh yeah, sure, that for sure. Yeah, it's again, like I would say one of the issues is that we also might be limiting the way we think about it and like how to calculate certain kind of parameters by using those circuits. So it's like adiabatic quantum computing like doesn't use the concept of circuits. You just get this like exponential. You check how like big the gap is basically in that model. So it gives you some different perspective on that. Okay, so I know we are out of time, so I wanted to say again, like, thank you for having me here. And I also wanted to say that if like, I'm pretty easy to find on the internet. So if anyone wants to talk, then like, please feel free to reach out to me.
Sure, thank you very much,
Yeah.
It's nice of you to come here and, discuss with us,
Glad to hear that. I hope it wasn't like too chaotic. But like the problem is like those ideas are pretty chaotic in my head as well. It's like not super well structured, but I hope like everyone got something out of this meeting. So
Yeah, I mean, they're essentially revolutionary ideas.
glad to hear that. And like I absolutely like, remember that I might be like absolutely wrong about many of these. So just like keep that in mind. It's like these are like random thoughts of like some guy who spent some time thinking on this, which might be as good as your thoughts on the topic. So totally kind of, be critical about what I said and like feel free to disagree. Cool.